section of Chapter 5, we're going to be looking at the idea of coordinate proof and working in the coordinate plane. Now, in a way, coordinate proof is a little bit easier because we can usually prove congruent sides pretty quickly using a distance formula. So distance formula obviously is going to be huge here. What we can't do necessarily is find the measures of angles in the coordinate plane, not with the level of mathematics that we know. It is possible to do it, but not at what we're doing. But the first thing we want to do is talk about how do we place something in the coordinate plane if we're going to use that, because we want to place it in a way that is convenient for us. So if I need to place a rectangle in the coordinate plane, I could put it anywhere I wanted to. I mean, I could put my rectangle up here, I could put it over there, I could put it anywhere I want in the coordinate plane and still get coordinates. But is there a good way of placing it? Is there a good way of placing this rectangle with the rectangle? There we go. And absolutely there is. I mean, the best way of placing the rectangle probably is to make it so two of the sides are right on the axis. Now my rectangle isn't perfect to a particular length, so I'm going to try to shrink it down here so it fits a little bit better. There we go. Come on, Mr. Rectangle, here we go. There we go. There's a nice little 10 by 4 rectangle. Because then now when we're setting things up, to use our distance formula, one of my points here is 0, 0. That's going to make life a lot easier. The other points are nice whole numbers. It's perfectly set up so that it's very simple to work with. All the coordinates, all the distance formulas, anything we'd have to do are going to be easy to work with. So setting up rectangles in the coordinate plane, choosing good placement is important. Rectangles are fairly easy to work with. How about when I'm working with an isosceles or a scalene triangle? Well, where should I put that? Well, it's a little trickier because, I mean, the way this is drawn right now, and I could put that vertex there, and it goes along the x-axis or the y-axis, and I guess that would be about as easy as it could get. But generally, what I want to do is set something up and place my triangle. So again, so the vertices are on nice points, and you know, I just drew this randomly, but they're right about there. So my vertices are all on nice points, and I start with one here at the origin. I'm not having to use negative points if I don't have to. I've got this point at 10, 0, and this point here is at 7, 4. So I could calculate lengths very simply because the nice positive whole numbers don't have to mess with negative numbers. Now, there are some times where you might want to mess with negative numbers. Say, for example, if you have an isosceles triangle that you're placing in the coordinate plane, you might want to, there we go, might want to set it up so that it's centered here on the y-axis. So this point, say, is 3, 0, and this point's at negative 3, 0. Notice how it's nice and balanced with this point here, center point here at 0, 0. Everything's really nicely balanced that way. So there are times that you might want to set it off into a negative portion of the plane. We don't always just want to put it in quadrant 1, but placing things in the coordinate plane, it's a bit of an art form and one we're going to get used to. We've already kind of done that, showing different ways of placing the rectangle that is still convenient for finding lengths. You can always assign new coordinates. If a square has vertices 0, 0, 0, m, and m0, find the fourth vertex. You're saying, well, wait a minute, what's m? I don't know what m is. M is a variable. We know it's hopefully some positive number. I know I have a vertex at 0, 0. So I'm going to define some distance out here as m, and that's going to be m0. I don't know if the scale is by 1s, by 1/8, by 16s, I don't know. But I know the same distance, if that's my scale of m, this is going to be 0m. Where is the fourth vertex of that square going to have to be then? We draw that out here. Well, the x-coordinate has to be the same as this x-coordinate. The y-coordinate has to be the same as that one. That's going to be at mm. See, a lot of times when we place things in the coordinate plane, we don't want to use specific coordinates, because when I prove something for specific coordinates, that's great. That proves it for that specific triangle. When I do something like this, where the coordinates are variables, now I'm proving it for a general case. Any square with side length m is going to have these properties, whatever properties I'm going to prove about. So instead of just proving it for a specific square, in fact, if we put those at 0, 5, 5, 0, and 5, 5, that would prove it for that specific square. But if I want to prove it for all squares with side length m, this is a way I can do it. I can work in the coordinate plane. Here I have an isosceles triangle, kind of what I had shown earlier. It says, write a plan to prove that SO bisects angle PSR. So I've drawn myself an isosceles triangle. I want to show that SO here is bisecting angle PSR. Now, in order to do that, I'd have to show that angle 1 and angle 2 here are congruent. How can I show that those angles are congruent? Well, what did we do yesterday? By showing their corresponding parts of congruent triangles. So if I show the two triangles net congruence are congruent, triangle PSO and triangle RSO are congruent, then I'll have those two angles congruent, which means that is a bisector. So let's write a plan for that. How are we going to do that? Well, I'd have to do what? How is the only way I can prove the triangle is congruent in this case? Well, side, side, side would work pretty well. So my plan might be, we know that SO is congruent to self. That's reflexive. Then use distance to show that PO is congruent to RO and PS is congruent to RS. Then side, side, side congruent triangles and angle 1 congruent to angle 2. Okay, if angle 1 is congruent to angle 2, that means SO bisects angle PSR. So that's kind of an informal proof. It's a plan for a proof. It's not the full formal proof. It's informal. It's kind of writing it. It's almost a paragraph style proof. A plan is more like a paragraph proof. We aren't doing all the formal steps and reasons. I'm not actually working out PO congruent to RO and PS congruent to RS. I'm saying use distance to show that. So I'm telling you what I would do. I'm not actually completing the task. I'm just writing out a complete plan for all the steps we'd have to take. And by the way, writing a plan is what we're going to be doing more and more of. Again, it's not doing the whole complete thing, but it's telling me what I would do. Here, given GJ bisects angle OJH. So GJ bisects OGH. That means that these two angles are congruent. Prove the triangles are congruent. Write a plan for that. And again, we start with our given. So given GJ bisects angle OGH, we know angle OG, sorry, I need the name of that point, OGJ is congruent to angle HGJ, reasoned definition of bisector. And GJ is congruent to GJ, reflexive. Okay, so I've got this side and this angle. I either need another angle, and again, it's hard to prove things about angles, but sides are easy to prove things about. So if I want to do side, angle, side, which side would I need? To do side, angle, side, I need GO and GH. So now show, or use it, you could say this, you could phrase it a different way. I'm going to say it right this way. Use distance formula to show GO is congruent to GH, and then triangles congruent by side angle side, because that's what we're trying to prove. And that's my plan. I don't even have to list the triangles. I can just say the triangles are congruent because we've already said what triangles we want to be congruent up in the instructions. So that's the plan. Again, if you would rather write out the full 2-column proof, you can. However, it does get messy when actually finding the lengths of the sides because you have to write out the whole distance formula. That's not necessarily so fun. Place an isosceles right triangle in the coordinate plane. Find the length of the hypotenuse and the coordinate of its midpoint, M. Okay, so we're going to need a graph. Oops. Come here. There we go. Now I want an isosceles right triangle. If it's going to be a right triangle, where are we going to put that right angle? Right at the origin. All right, I need it to be isosceles and right. So I'm going to go ahead and make that many units long and make this exactly the same. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, and there's my right triangle. Now, I don't want to necessarily, I guess I could assign coordinates. It doesn't say exactly where it should be. So let's go ahead and call this 5, 0. This is 0, 0. This is 0, 5. It said find the coordinate of the midpoint of this. Oh gosh, that's in the middle of nowhere. What could I have done maybe to make this easier if I need to find a midpoint? How could I have made this a little nicer? Maybe if I'd have gone out to an even number. Because even numbers divide evenly by 2 and I'm looking for a midpoint. And where's that midpoint going to be right now? It's going to be right there at 3, 3. Because this is 6, 0, and this is 0, 6. I found the coordinates of the midpoint, and I need to find the length of the hypotenuse. The length, the distance is from 0 minus 6 squared plus 6 minus 0 squared, or the square root of 36 plus 36 is the square root of 72, which is the square root of 36. Sorry, that was a terrible 3. Times the square root of 2, because 72 times is 36 times 2, or 6 root 2. So the length of this side is 6, the length of this side is 6, the length of this side is 6 root 2. That's interesting. What if I generalize this? If I generalize this, instead of using specific coordinates, what if I just used like A and B? Okay. So what if I said that this is 0, 0 still, this point is A, 0, and this point is 0A? Then what's the coordinate of this point? The coordinate of that point is A plus 0 over 2, or A over 2, A over 2. What is the length of that diagonal? The length of that diagonal, A minus 0 squared plus 0 minus A squared. So the distance is the square root of A squared plus A squared, which is the square root of 2A squared. But that's the square root of A squared times the square root of 2. The square root of A squared is just A times the square root of 2. So the length here is A root 2. How long is this length? 0, 0 to A is 0. That's just A. And that's A. That means in any isosceles right triangle, for any isosceles right triangle, the length of the legs are the same, and the hypotenuse is the length of the leg times the square root of 2. That midpoint is exactly at 1 A over 2, A over 2. But the more significant conclusion comes from the length of the sides. The two legs are the same. The hypotenuse is always the length of the leg times the square root of 2. That's going to become very important to us later, this particular fact. We're going to see that again. So coordinate proof, it's a little bit tricky. We'll have plenty of time in class to look at it. We're going to spend 2 days looking at it. So if you're not getting it all the first day, give it a little time. We'll catch up to it the second day.